Marquez, co-founder of Arduino. Let me just fix the camera for a second. And I'm streaming live for the third day in a row, I think. I'm working with the project. I'm making a project. This is the European Maker Week, so I decided to start working with a project to make it a bit more interesting. Oh, I just realized I turned off the sound right now. I was still having the music around, so I will just start from scratch so I can cut it later. So hello everybody, this is David Cuartiez, co-founder of Arduino, and I'm here right now transmitting at the European Maker Week. This is the third project, or the third program on a topic that I'm doing. I'm experimenting with what it means to make kind of like a docu-soap of building a project step by step in 1 hour episodes. I will just very briefly, in a second, I will briefly introduce you to what it is that I'm doing. Just before I continue, let me remind you that this is the Arduino LiveCast. It's typically running live every Thursday evening at 7 p.m. CEST. But well, if you are in somewhere else in the world, will be at a different time in the day, obviously. And we're going to be running this program for as long as we can, and we have some scheduled programs with interviews, we have some scheduled programs with demonstrations and so on. What I'm doing this week to commemorate European Maker Week is to make a daily live cast where I'm trying to solve a project that I basically took from a box randomly. In particular, what I'm doing is that I'm working with, I'm going to just show you this. This is the big mess that I have on my desk, and this is what I am working with. Well, actually my camera froze, so you just see a frozen image. Maybe if I change camera to this one, oh, that camera is also frozen. This is interesting. So let me just very quickly troubleshoot this thing, because I would like to be able of showing you what's going on. So this one, okay, there you go. So now you see, yeah, that camera is working. I will just make sure I have the flickering effect. And the other camera, which is the special camera for close-ups, which is this one, I will also deactivate and reactivate. And now, yeah, you see my hand. Okay, perfect. So now I'm really live. So that's basically what I'm doing this week, step by step, learning about this shield here that is made by Nootropic design, and it's called the AudioHacker. And we made it to the step where I mounted everything 2 programs ago, and it's 2 shields. One is the Nootropic design AudioHacker, and the other one is the Nootropic design controller that you can see here now. And includes potentiometers and buttons and a couple of LEDs for you to implement sound loopers and things like this. And again, because somebody asked me the other day, I have absolutely no affiliation with Nootropic design. I bought this randomly on the internet almost a year ago because I found it and I liked it. And the thing that I'm doing here is to basically make a project like the same way you would make a project. And what I'm trying to learn is how it works. And I'm facing some challenges. So the kind of challenges you face every time you make a new project, like, okay, I bought this thing, I was very excited, I saw the video what it does, but then for real I have no idea how it works. And I'm basically learning how to make it work. And yesterday I was trying to experiment with software, and the thing that I did is that I make a couple of Arduino programs, and I'm going to show you these Arduino programs that I was working with. This is let me just open the program we have from yesterday, this AudioHacker, and this is the program I have from yesterday. And I was trying to write values to the DAC. And for those of you that just hook up into this program for the first time, it might take you by surprise and you might not know what I'm talking about. Well, the AudioHacker shield is actually a device. It's pretty impressive. It has a bunch of things on it, and they are a DAC, which is a digital to analog converter that will allow you to take sound samples and send them out to a sound speaker. It has an ADC, which is an analog to digital converter that will allow you to take signals that come out from an audio jack and transform them into digital signals and use them. And it has a RAM memory, which you can use to like store the data and then play it back. And that will allow you to do things like adding echoes and other kinds of effects. And an operational amplifier that will allow you to, for example, connect headphones directly to the audio output, which is here, and listen to how it sounds. And you might have realized that if you take a look at the solder view of things, that all of the chips are put already there. I troubleshooted this thing. I'm 100% sure that everything is connected. And there is a couple of audio jacks. One is for audio output, and I have a mixer board that I can use to listen to the sound. And the other one is an audio input that I can use to bring in sound. And I basically failed to run some of the basic examples because I didn't read any of the documentation whatsoever. So I just tried to do things the way I try to do things. I like to try things out when I build my own projects, and well, it failed. So I need to make some research to see how this could work. So I decided to just experiment with software a little bit, and so I wrote a small program yesterday that what it does is that it starts the library AudioHacker, and I read in the documentation, which is here, that there is a couple of functions that you can use. Like there is a begin function that starts everything, the read ADC that reads the analog to digital converter, and the write DAC that writes signals out. And I thought, well, if I have an Arduino board where everything is connected, I can make a program that can write something to the output, and then I could read to an analog pin and print it out over a serial port to see how it looks like. And so this is the program that I wrote, as you see here. On the other hand, I also experimented with something else. This is an alternative loop that I did, where I thought I could also just try to read an analog signal and print out the value with the ADC, and I could put voltages by taking the 3.3 volt or the 5 volt connections from the Arduino board and push it out to see how things look like. And both failed miserably. So the question is, why did they fail? And well, even though I said I was not going to work with this after I finished the program yesterday night, of course I'm very curious, and I did one thing that I hadn't done until then, which is to read through the code. This is very important because reading through the existing code will allow you to learn about what is that works and how it works. And so I opened an example that I have already opened here yesterday, which is the echo effect. An echo effect is one of the various examples that come with the AudioHacker library, and so you can go to files and check on AudioHacker which are the available examples, and there's a bunch of them. So I just took one of them, which is echo effect. I could have taken any other example. I just took this one randomly, and I took a look at how it looks like, and I'm gonna very quickly read the code for you. So first of all, it includes the library AudioHacker. The AudioHacker library also creates an object, which is the AudioHacker object that you can then use to instantiate all the different methods. Then it has the possibility of includes here a define that is used to use a serial port to print things out. It's a very common technique. I don't know if you ever used it. You can then comment this away, and if debug is declared, then you can use this as a way to include different functions. Then there is different variables that are declared: a playback buffer, sample rate, read buffer, write buffer. So you can, if you're into sound, you will understand what these different things mean. If you're not into sound, let me just very quickly tell you what it is. Sample rate is the amount of samples per second at which things are sampled. I can later on make some drawings about how digital sound works, just to help those of you that don't have an experience in this. But you can imagine that basically you have a sound that is an analog signal, and you take samples of this sound, which means there is moments in time where you decide to just sample and record the value of the input. And the sample rate indicates how many times per second you are taking signals from the input. Then read buffer, I understand that is a place where to store the data that comes in. Playback buffer is I understand is a place where to take data from memory to play it back. And write buffer, I understand that is a place that you use to write to the memory. But this is there is no explanation in the code, so this is a way I am assuming this works. Okay. Then there is I realize there is some timers here, and this is interesting because this means that time is being accounted for in order to do some operations. And even though I don't know what it's going to be doing yet, we will see it later. I mean, it's important because this means that some things are happening in parallel. That's why you use timers instead of just using delays in your program. And then I see there is some other information like memory addresses and last debug print that I guess is used to decide whether the latest information has been posted out or printed, or it should print something else. Okay, so in setup, I see that if debug is activated, then I should be using the serial port at maximum speed or at 115,200. And then I see it declares here some values, playback buffer 2048. I'm assuming this means that this is the size of the buffer. I don't know. Sample rate, default recording sample rate. So it's taking a default value from the library, which I don't know what it is. Timer start, it takes a number that is based on the speed of the CPU, which is 60 megahertz divided by the sample rate. So this is telling you when it's going to be starting the timer, and starts the AudioHacker library. And what it means to start the AudioHacker library is something I don't know, because I haven't checked the library, and we will check into the library today, trying to reach an understanding on how this thing works internally. But I'm assuming that what this thing is going to be doing is to be establishing some default values to transform your Arduino board into some sort of synchronous sound machine. And this means that it's going to be sampling time, and at each one of those instances of sampling time, letting you do things like reading the input, write the input to the memory, read the memory and send it to the output, read two different sound samples and add them or whatever. This is basically the way I expect it to work. And the default recording sample rate, it will be a timer in memory that will be executing some sort of like a time interrupt to do sound operations. And again, if you don't understand what I'm talking about, please bear with me. I will explain this. I will make a drawing later and explain which is the way I understand this thing. And again, if you're an expert in this, well, you're welcome to continue with us, obviously. What I'm going to be doing, even though I know everything, not everything, but a lot about digital sound, I'm going to be playing naive today because my idea is to very slowly build an understanding how this works. So let's just see how I will then continue to do this. So then if the debug is activated in the setup, I will just print out which is the sample rate, just to give an information to the person using this example. Okay, then in the loop here you see, first of all, it runs a small delay, and then it's printing out, sorry, it's reading the analog input on 0, and this is supposed to be a potentiometer of sorts. Probably is the one taken from the other shield that is clearly connected to analog 0. If I look at it, actually it's not connected to analog 0, it's connected to analog 1, analog 2, and analog 5. Oh no, yeah, analog 0 is down here. Okay. Yeah, so basically what this thing's doing is that it's connected to analog 0 and reads that value, and that will be the delay for the echo. So you know how echo works. If you record a sample, you say hello, it will take the sound sample, delay it in time, and reduce the amplitude. So it will be like the signal went somewhere, bounced, and came back. And the delay is the time that it will take for the sound to fly to the other place, bounce, and come back. It's like when you scream in the mountains, you hear the sound bouncing in the valley and returning to you, and the delay between when you say something and when it comes back is a product of the distance. If you saw the LiveCast where I was explaining the ultrasound sensor, this is exactly the same principle. And then if we are debugging this thing, then it will decide whether it's going to print information, and it will print information only once per second. This is what this means. It's calculating the time, and the last debug print timer is checking out that the difference of time is bigger than 1 second. If that's the case, it's going to print out all the information it has, and it will print out how long the delay is, how many milliseconds for even cycles, and how many milliseconds for odd cycles that it takes to push out the sound. And here's where the surprise comes. And this is something I hadn't done before, and probably this is the reason why my program wasn't working yesterday. So there is this ISR, and it's the method or the function that is used in the AVR chips to service interrupts. So this is a function that you have to declare that is typically empty, and you have to override it, add content to it, and what this will do is to then allow you to do operations. When do you do these operations? You do these operations, I assume, every time the sample has to be taken or written or whatever. So this means that your Arduino board is not going to work the same thing or the same way it would usually work, because it's using the timers in a different way. So there might be some functions that might not work, like for example delay. So this is very important, because you need to keep this in mind when you're writing your code. So yesterday I was calling these functions to read signals or write signals inside the loop, but most likely I cannot call those functions inside the loop. Most likely I have to call those functions inside the interrupt function, which is the moment when the system is enabled to check out the DAC or the ADC or any of those things. Again, I'm assuming this is the way. And as you see, inside the interrupt function is when this is finally calling AudioHacker write DAC or signal AudioHacker read ADC. So this is the place where we can most likely read and write from the digital to analog converter, or sorry, to the digital to analog converter, or from the analog to digital converter. And so how am I going to do this? I mean, there is the rest of the program here, and it's an echo. It's basically taking signals, writing them to memory, and so on. So, you know, we could go into exploring how the different parts of the echo works, but I think it's not relevant at this point. The important thing here is that I realized that there is something that I was not doing yesterday. Because if I look at the program I had yesterday, it was this one, test AudioHacker. I'm gonna make it a bit smaller and put it on the side, so you can compare the basic aspects of this program, and you will realize how I was very much not doing that. I just want to pin this application here like now. So in my program yesterday, in the loop, I was trying to do the operation of counting between 0 to 155, write this to the ADC, read the analog value, and print it out. And this clearly didn't work yesterday. If you remember, I tried this out and I failed. So that's what got me to think, okay, what is that I am doing that, or that I am not doing, sorry, that the program is actually doing, that the examples for Michael are doing, because Michael showed us a video where everything worked, and I just want to replicate what Michael's doing. So I am assuming, and I have a certain degree of certainty that Michael's things work perfectly. So if there is a failure in my setup, it's my failure. So I need to figure out what is it that I'm doing wrong. So so here in the screen right now, you have on the left hand side the timer operation, or the timer function that is triggered by a timer interrupt every certain amount of times per second. On the right hand side, what I'm trying to do, and I'm trying to call this AudioHacker functions directly from the loop, and I know it's not working. So just to show that this is not working, just to highlight it even better, let me remind you the setup of what we're having right now. So this is the setup. We have the Arduino board is behind her. There's the shield on top. This is here is the output signal. So I'm trying to write to the DAC a signal that will change between 0 and 255, which will be between certain values in analog signals, and then I'm trying to read that from an analog input down here on A5 in the shield, and I'm just trying to print that value. So, and then I'm making a delay to see how this works. So the question is, I know that Michael's system is using timer 1. What else is working on timer 1 on Arduino? I don't know this by heart, but we can check it out. We can Google this, and we can just figure out whether there is anything else that is working on timer 1. So let's see, Arduino. My keyboard is not really working. I think it's running out of batteries. Arduino Uno, timer 1. Okay. This is from the Arduino Playground, which is community maintained documentation. And it says here, timer 1 is a collection of routines for configuring the 16-bit hardware called timer 1 on the ATmega 328. There are 3 hardware timers available on the chip, and they can be configured in a variety of ways to achieve different functionality. This is meant to be doing some changes on PWM, but this is not what I'm looking for. Then timer 3 is meant to be for the Arduino Mega, which is giving you the possibility of having timer interrupts on the Arduino Mega to do other things. Again, this is not what I'm looking for. So what else do we have here? Oh, look, there is some information here in Hobbytronics that made a pretty good article, now I remember, some years ago about the timers. And let me just make this bigger. Okay. So you see there, timer 0 is an 8-bit timer that is used by delay, millis, and micros. Timer 1 is a 16-bit timer that is used by the servo library. Timer 2 is an 8-bit timer that is used by the tone library. What this means is that the different internal timers in Arduino are used already, in the Arduino Uno, are used already by the default Arduino core. If we overwrite them, like this is the case here, then there is some functionalities we might be losing, and things will stop or will cease to work. Plus, there might be some other things that might not be working. So what happens then, since AudioHacker seems to be working according to the examples that we had, let me just go back to the this view so that you can see the Arduino code. So we have the echo effect, which is the example that is supposed to be working, and the one we made yesterday. And we see that this one, the echo effect that Michael made is making use of the timer 1. And mine is not making use of the timer 1. So this means two things. If AudioHacker, the AudioHacker library, is making use of the timer 1 to operate, and I'm not doing that, my code will most likely not work. That's the first thing. The second one, if timer 1 is being used, when those events are happening, if I'm not handling the interrupt, some things might not work. Like maybe some of the other timers might get broken because I'm not handling the interrupts properly. So this is really a challenge. So at this point, at some point I need to read how the library is inside. But before doing that, I still want to try things out without reading inside the library. So what I'm going to do is that instead of running this code inside the loop, I'm going to try to run this code by myself, but using the timer as it's being used on the echo effect example. So in order to do this, what I would do is to take this here, and I will paste it here, and I will leave the loop empty. And I hope this will help for those of you that never saw a timer interrupt. It will help you understand how this works. So as I said, clearly the AudioHacker is setting up some sort of timer, and it's been executed a certain amount of times per second. And clearly that every time that happens, there is a timer interrupt function that is triggered and is used to read some information or do something out of it. So again, then my loop can totally be empty because I'm not repeating the operations all the time. The operations have been repeated whenever this time things happen. And whenever this time event happens, this timer event is triggered, I will then try to do this whole operation here. Okay? So let's see if this works. Let's see if this works. I mean, let me anticipate for those of you that know already about interrupts, because you might be thinking that it is crazy. Well, we know it's not gonna work, okay? But let's just continue to do it for the sake of those that are learning about how this works. So I will just directly compile and upload. I have everything as I had it yesterday. This is Arduino Uno, and this is my COM5 port, and I will just upload it to my board, and let's see what I get when I read the port. Oh, I think I made a mistake. Yeah, I lack in a curly bracket. Here we go. So you have press Control T, and there you go. So, okay, it's been compiled, it's now being uploaded, and it's running on the board. So if everything was working fine, every time this is triggered, it should be giving me, it should be printing out 255 values to the DAC, and I should be able to reading them and print them out on the serial port. I open the serial port monitor, and this is what I get. And data is flowing really fast. So I would say, like, okay, I can really read what the data is doing. What if I just increase the delay to see whether I can make this go slower? And again, those of you that know how interrupts work, you know already what's going on. Okay, I'm just gonna do this for the sake of clarity and explain this to people. So if I increase the delay, theoretically, I will be making this thing go slower, and this will allow me reading what's going on. But you see, I increase the delay, and it keeps on going super fast. What if I make the delay even bigger? I make the delay even bigger, and look at what happens. It's gonna run at the same speed. And the question is, why is this happening? Well, this is happening because when I enter an interrupt handling function, I just service an interrupt handling function, the delay is working through a timer, which is timer 0, as we saw, that is disabled. When I ever enter an interrupt timer function, I'm disabling the other interrupt timer functions of happening. And so this means that delay is not going to work because it needs a timer to work. And this is what you see here. It is not working. So what else can I do for eventually slowing this down? Because I would like to read the data and see that whenever I write something to the DAC, I can read it back. Well, there is a trick, because while delay is working with a timer, delay microseconds is actually done by just doing some junk operations in assembly. So, sorry. So they're stopping the system for real. While delay is just putting a watchdog and waiting, delay microseconds is just counting for, I think, if I remember right, 4 or 5 operations. So I could do something like this. Because delay microseconds is not using any timers, I could just tell delay microseconds to wait for a while. But if I do delay microseconds 1000, this would mean 1 millisecond, so it's still very slow. So I could use another 4 that it's going to be counting, for example, 10 milliseconds, 100 milliseconds. So I will just make it smaller than 100. So this will count 100 milliseconds with the difference, and again the difference between this one and the previous one is that delay microseconds is not using a timer, so this will for sure slow down the flux of data to the serial port. So look at this now. You see, now we can read the data, and we can see it goes up to a maximum of 420 something and to a minimum of like 100 and something. So this is very interesting. So now finally I can see that really writing to the DAC works, because I can read the value as it comes back to the Arduino board, and I can see how it looks like. So, okay, I can confirm the DAC works fine. And the only thing I had to do to make this work was to change the way I was assuming things were working. I was assuming that these functions were just working as normal functions, but they are depending strongly on the timers. And if I don't make it run in the timer, then they don't seem to work. So then still the question is, how do they work inside of the library? Because until now everything I've done has just been purely empirical, sorry. So I haven't really read the documentation in depth. I have only experimented with things because I think it's fun. And there is nothing bad about it, but there comes a time when you need to read the documentation in order to build an understanding of how things work really internally. And this is, in my opinion, that time. So I have learned already that this thing works using timer interrupts, and when I call the functions inside the timer interrupts, that they work fine. So how does the library look inside? Let's take a look at that. I installed the library the other day, if you remember, directly after soldering the kit. So what I'm gonna just check is inside the browser, and I will just take a look at the GitHub for this project. And the GitHub for the project is here. There you go. This is the GitHub for the project. I will just make it a little bit bigger so you can guys see it better. And it has only two programs, or two files, sorry. One is the AudioHacker.h, which is the definition file for the library, and the other one is the AudioHacker.cpp, which is the one that does the thing. So AudioHacker.h is made in 2013. Again, Nootropic design, has the copyright of this. This is under GPL, which means it's actually GPL 3. So it means it's free software, so you're free to use it, modify it, redistribute it, etc. And this library, if you remember, the program I made explaining how the different libraries work, it starts defining AudioHacker constant that makes sure that you don't load the library memory twice. It includes a library that includes different types of integer numbers. It makes sure that it has Arduino.h. This first part is for Arduino 1.0 or bigger. W program.h is how it was called for Arduino smaller than 1.0, which is already some years ago. Defines here the maximum size for integer numbers with 16 bits. Defines, I assume this is the chip select for the different memory chips, the chip select for the DAC and the chip select for the ADC. The chip select, for those of you that don't know what it means, is the pin that enables that particular chip will work. So that will activate the enable pin in the chip. Typically chips have an enable pin. And here we see that it's using a clock pin, meso pin. This basically means it's an SPI kind of communication that it's using. And it seems like there is SPI communication for everything. Okay, so it's using different pins for the RAM 0, the RAM 1, the DAC and the ADC, and it has a single pin for reading from all of them, and a single pin for the clock. And these are how you activate, and we just highlight, this is how you activate and deactivate the clock pin, just to trigger a 0 to 1 change or a 1 to 0 change. And this is a little bit low level, and in essence what this is doing is that I will make a drawing later on to just summarize what we are learning today, really the findings of today. But what we're checking here right now is that all of these chips seem to be working through an SPI port. So they have a single, and they share a single pin to read the information back into Arduino, but they have different pins to send the information up to Arduino. As well, they have a single clock pin. So all of the chips seem to be having a single pin to control the clock to all of them, so they are synchronized between all of them. Okay. Then there is some information here on, well, what you see here is which pins correspond to these different readings. This is how you do define writing or reading or a pin number at low level. So this is pin D12 is the one for reading, D13 is one for the clock, D10 is to select and deselect the RAM 0, pin 9 is to select and deselect RAM 1, pin 8 to select and deselect the AC, and 7 select and deselect ADC. For the Mega board is different. What we just saw was for the Arduino Uno, 2009 and 10.000, and Leonardo is yet again different, so they fall in different pins and so on. Then the DAC chip has different configurations, and here you see is telling that it has to have this number to define how it's going to work, and it has a variable to store, which is going to be the maximum address for the memory chip, because the address range for the memory chips we have is between 0 and 131,067, which is how much data you can store in one of the chips. And here's a small explanation on how this is cut through. Then this information is different for, there's some information here that is meant for the Mega down here, which is a sample rate, but we don't use the Mega, we use the Uno. So this is our information that is valid, which is that for the Uno we have a default sample rate of 40 for 100, sorry, which is the typical sample rate that you will use for CDs, and the default sample rate for 8 bits is 42,000. So if you work at 16 bits, you have to go slower than if you work for 8 bits. And by default, the recording sample rate is going to be 22,050, which is exactly half of the sampling rate for CDs. And this sound quality, for those of you that are not experts or not used to talk about how sound works, is a pretty okay sound quality. So many of us don't distinguish the difference between a sample rate of 22,000 versus a sample rate of 44,000. You need to have a somehow trained ear to be able to really noticing the difference. And personally, I don't notice a difference, but I'm also not a sound connoisseur. I'm just a sound digital engineer. So, and here you see, this is no EP or NOP, is not operation. This is how you in assembly you do an operation that is just taking one clock cycle. And this is what I said that microseconds, delay microseconds, is just doing some of these knobs. Just doing some of these knobs that account for the amount of time that a microsecond lasts. So you can imagine if the clock in Arduino is working at 60 megahertz, you have to do a bunch of those in order to a bunch of knobs that will take one clock cycle in order to account for 1 microsecond. So until here is all constants declaration, and then we go into the proper class declaration, which includes all of the methods that are used. And we have one to begin, which will configure everything. We'll try to see later how it looks like. Then there has one for reading the ADC normally and in 8 bits. As if you remember, the default configuration here is 12 bits, so it's pretty high quality. I said 16 bits earlier, I was mistaken. I actually meant 12 bits, which is the maximum resolution of this system. Then you have write SRAM, and you have different functions to write to the RAM. So you can write to the chip number 0 or 1, the address, and just 1 byte of data, or you can write a certain buffer of a certain length, or you can write an unsigned integer, and you see there's here a way to write a pack number where you add two different integers. So there is different ways of reading and writing basically. That's for the RAM, and finally you have write to the DAC. So these are the basic methods for the class. And then there is here some constructs that are used to make low-level operations. And you see here, for example, this one makes no operation, no operation, no operation, clock high, no operation, no operation, read the memory, clock down. So these constructs will be called in order to make basic operations like you see here, reading a bit, write to the SPI, and so on. These are functions that are going to be called from the CPP file, which is the one that contains the proper contents of the different functions. So right now, if you remember, in our Arduino code here, we were, well, I said here, but I didn't show you here, we were calling write DAC 8-bit. So how does write DAC 8-bit work? I'm looking at the time. I think this is going to be as far as I will be able of going today, because I will not make the program longer than an hour, just for the sake of mental health of everybody. But I'm going to be checking how write DAC works, and then I will just make a quick drawing summary of everything we learned today, because it's actually quite a lot. So write DAC, in order to see how write DAC works, I need to go back to see how the CPP file defines write DAC. So first, I will need to look at two different functions, because in my program I'm using the begin function, and then I'm using write DAC. So let's take a look at first begin. And begin starts by making a series of operations. So it declares the pins for the clock, master input, serial output, slave output, sorry, master outputs, slave input as an output, and so on. So these are the pins for the basic SPI on Arduino. Then it writes the clock down, it writes the input down, and it writes the output down, and it writes the chip select high. So the question is, why does it write the input down? Okay, so I'm gonna let that question there open for you, because if you know a bit about low-level Arduino code for AVR, this is actually for AVR. Remember, we're talking with AVR, we're not talking about the SAMD21 or the ARM technology that comes on the latest Arduino boards. We're talking about the legacy products. If you declare a pin as an input and then you write it high, you're automatically configuring the input pull-up resistor, what allows you to just detect that you are triggering the pin by writing to 0. So but if you're writing an input to low, what are you doing? So I'm gonna let that question there. You're welcome to answer it on the chat. I remind you that we have this chat running. You can see it on the top right part of the window. And if you click on the if you go to Discord, you're welcome to answer the question on the LiveCast channel. So then we declare the different pins for the SRAM, for the DAC, and for the ADC. And you see basically we declare the chip selects as outputs, and we write them all high. This makes me think that by default the different pins are not listening to SPI if the chip select is high. It makes me think. I haven't checked the data sheets for the different chips, and that could eventually be interesting if I have to continue troubleshooting this library in depth to take a look at the libraries, at the datasheets for each component and try to understand how they work in depth. So then I configure the SPI. This is a configuration of the SPI at low level inside the AVR memory. So first you enable the SPI by writing the pin in a certain way. Then turns the SPI interrupts off to be able of writing to it. Say that you will make you will send the most significant byte first, then you configure it as master, then you explain that you're gonna read or write with the leading edge. You see this is for both here. So then you sample on leading edge, then you declare the clock, and the speed of the SPI is going to be 1/4 of the clock time, which means the SPI will work at 4 megahertz. And then you configure the option of double the speed down here. Then you disable timer 1, very important. As I said earlier, if you are using this library, you cannot use the servo library because servo library is completely built on timer 1. So it will stop functioning as you expect it to work. And as we saw earlier, timer 1 is a 16-bit timer. And you just configure the different options for timer 1. And then you end up enabling the timer 1 interrupt. This means that at the end of begin, the timer 1 is going to be counting time based on a variable which is going to be the default sample rate. And this is going to be ticking at the default time rate. And that's how you have to operate. You just have to take that into account and know that this library is going to be operations when that happens. So as it says here, there's some legacy code in the library, and it says that the old code was working SPI at 1 megahertz. This one is working at a faster speed. And so we entered to look at the different functions, and there are some explanations here. This is very interesting because this is actually the use of this library, and this is, I think, this is the mastery that Michael has been putting here to make everything fit. And it is, for example, that the MCP3201 ADC has a maximum SPI clock speed of 1.6 megahertz. It means that if you're working at 4 megahertz, it's not going to work. So that's why in the legacy library, in the old one, he was working with SPI 1 megahertz to make sure he could work this out. But in the new library, he has written his own SPI functions that we saw in the .h file earlier that allow him to speed it up to 1.6 megahertz. And in order to speed it up, what it does for real is to make it work at a faster speed, and then adding knobs, not operations in assembly to, slow things down. This is my assumption, but I think it's how it works. So the real function we're interested in, because it's the one we're using, is write DAC 8 bits. So let's stop talking about the ADC and go to the write DAC, just to make sure we are looking at the thing we want to work with. And here it is. This is the function we are calling. So first we select DAC, and select DAC just triggers the chip select for it to be active and activates the chip. Then writes to the SPI the configuration information for the digital to analog converter that we saw in the .h file, and it writes a signal, and the signal is the value that we are sending as data here. So it has to cut the information in two pieces. First, it sends the configuration with half of the signal, and then it sends the other half of the signal down here. And then it deselects the DAC. Okay, so basically it takes the chunk of data we're going to send, for example, the number 123, and it cuts it in two halves, the lower part and the higher part, because our numbers are 8 bits, so it takes 4 bits and sends 4 bits with the configuration first, and then it sends the lower 4 bits. So this is how it works. And So at low level, now we saw and we understand how this is functioning. And the question is, will it work for other parts? We just saw how it works for writing, and we saw that it actually works. But will it work for reading? Reading from the ADC? Because this is the part that I seemed not to be working yesterday. Well, that is not anything we're going to try today. I just wanted to give you an introduction to the timer function, in particular for this library, and see how it works, and see a trick so we could, even though we're using the timer, slow down the information so we can see it. Obviously, by slowing it down, we make the whole idea of the DAC not really usable, in the sense that if we wanted to, for example, play a sound, we should not be using this whole idea of the delay here, because it will not allow the sound to be pushed out at the right speed. But in our next program, we're gonna see how we can, I mean, we have two routes. We can, for example, see how we can play a sound, or we can just troubleshoot to see whether the ADC works. And in order to finish this program in a nice way, what I'm going to do is to just make a drawing of everything that I said. For those of you that are a bit new to this whole idea of digital sound, I might not understand what we are talking about here, just because I want it to be clearly understood, because it will allow us to make other experiments in future livecasts. So let me just add a piece of paper here and center the camera. Okay, look a bit nicer. There you go. And yeah, I suspect that it's not very, it's a bit blurry right now. Yes, because why should it be clear? Okay, now it's focused. Okay, I think I will disable autofocus on the camera. Here it is. Camera control, not autofocus. Okay, so now it's a lot more clear. So what I'm gonna then is quickly explain, make a quick summary of everything we've seen today, and see, just to clarify things for those of you that are new to this topic, and make sure that everything is more or less understood. So we saw that sound is analog. This is the first thing. And this means it's a signal that goes like this. And what we do is that we sample it. We sample it. And this means that every certain amount of time, we take points, and these points is what we bring inside the microcontroller. The sample rate is the amount of times per second, the times per second we are checking things, the sample rate. So this is crucial, because this is how AudioHacker is deciding where to check for sounds. So it's a sample rate, and we saw that the maximum sample rate we're getting in our shield is so the default sample rate we get in our shield is 22,050, which is pretty good, I would say. But we can get a maximum sample rate of 4,400 when we work with Arduino Uno. So there's different chips on the board. This is something else we learned. So there's the RAM chips. There is the DAC, digital to analog converter, and there's the ADC, and all of them are working over SPI. In order to make it as fast as possible, we're making the SPI work at the clock frequency divided by 4. It's something we saw in the libraries. The fact that everything is SPI, it means that the whole circuit is synchronous. This means that all operations are happening at a certain pace, which is basically the whole idea of the sample rate. It's synchronized with the sample rate. And in order to work with the sample rate and do this synchrony, we're using timer interrupts. And these timer interrupts, what they do is they trigger an event every certain amount of time, and you have to override the function that is supposed to do something when that event happens. And that's what we do with this whole ISR function. This is the ISR function. Okay, and then we learn a trick in order to be able of checking what is happening when you're working with a timer interrupt, and is that even though the timer interrupt disables delay, it cannot disable delay microseconds, so we use delay microseconds. Okay, so this is what we learned today. This is a very complex thing. As we are going in the series, we're slowly unveiling more and more things, and you have to put into circulation a lot of knowledge that I said from the beginning. This is not a beginner's LiveCast, this particular series, but I hope it will be good enough for some of you to get started with understanding how digital sound works, how low-level signals work, like how you use SPI to control different things, how memory chips work, and how analog digital conversion and digital to analog conversion works. This is it. So thank you very much for today, and I will most likely make my LiveCast in just 12 hours. So those of you that are interested in following the series, there's going to be another program tomorrow. It's just that it's not going to be 8 p.m. CST. It will be most likely at 8 a.m. CST. And the reason for this is that in the evening tomorrow I will be traveling to Madrid, and I will be attending RoboCampeones, which is a competition in robotics that is arranged by a bunch of teachers that make a yearly competition in robotics. And I will be interviewing a bunch of kids building robots with Arduino. And I will unfortunately not be able to do that live on Thursday morning because the internet connection is not that good, but I will bring my whole gear and I will record the program as if it was live and broadcast it in the evening. In parallel, I will continue to work with this project that I'm working, so I will bring things with me and continue to find time to continue to livecast my next finding. So the AudioHacker Shield is going to be my ongoing project that I will use to fill in different times in the week. I hope you're liking it. Please give me feedback on the Arduino Discord chat channel. Send your thumbs up on YouTube, and please subscribe to the Arduino YouTube channel. Thank you very much, and see you in 12 hours. Goodbye.